Hi, and welcome to Section 4. In this section, we're going to look at feature engineering. Feature engineering is one of the most impactful things you can do to improve your machine learning model. We'll now look at what it is. There are two things that can help make your models more successful. The first is feature selection, and the second is feature extraction, or the process of creating features. In feature selection, you select the most relevant features and discard the rest. You can apply feature selection to prevent redundancy or irrelevance in the existing features. You can also use it to limit the number of features to help prevent overfitting. Feature extraction builds valuable information from raw data by reformatting, combining, and transforming primary features into new ones. This process continues until it yields a new data set that can be consumed by the model to achieve your goals. As the diagram shows, feature extraction covers a range of activities, from dealing with missing data to converting text data into numerical data. Although the list isn't exhaustive, it should give you some idea of the data handling that's needed to get data into a useful state. Many of the tasks are no different than any other job working with data. You'll want to make sure data is in the correct format, that it's consistently represented, correctly spelled, among other tasks. For example, you might combine data or extract data into multiple columns. Or you could also remove columns altogether. Specific to machine learning, you'll need to convert text columns to numerical values. You'll also need to decide how to handle outliers and potentially rescale your data. Next, we'll look at some of the more common tasks in this section. Most machine learning algorithms work best with numerical data. You'll need to make sure that all columns in your data set contain numeric data by converting or encoding it. You might need to make several passes through the datasheet before you can encode it. For example, you might have variability in the text values, such as rows that contain both medium and MED as values. If the categorical data has order to it, you'll want to encode the text into numerical values that capture this ordinal relationship. Say you have data showing maintenance costs. You might encode low to 1, medium to 2, high to 3, and very high to 4. After you've made sure your categorical data is all uniform, you can use tools like scikit-learn and pandas to encode your data. If the categorical data doesn't have any order to it, then you'll need to break the data into multiple columns. This will help make sure you don't introduce an ordinal relationship to the data that isn't there. For example, suppose you assigned a value of 1 to the first color, such as red, and you then assigned 2 to the next value, say blue. The model could interpret blue as being more important than red because blue has a higher numeric value. Encoding non-ordinal data into multiple columns or features is a better way. Think of the new features like a checkbox. Consider the example. There are 3 features that were generated. The value 1 indicates that the instance has that feature, like its color. That's it for this section. We'll see you again in the next video. Hi, welcome back. We'll continue exploring feature engineering by reviewing how to clean your dataset. In addition to converting string data to numerical data, you'll need to clean your dataset for several other potential problem areas. Before encoding the string data, make sure the strings are all consistent. You'll also need to make sure variables use a consistent scale. For example, if one variable describes the number of doors in a car, the scale will probably be between 2 and 8. But if another variable describes the number of cars of a particular type sold in the state of California, the scale will probably be in the thousands. Some data items might also capture more than one variable in a single value. For instance, suppose the dataset includes variables that combine safety and maintenance into a single variable, such as safe high maintenance. You'll need to train your machine learning system for both variables, and also split that single variable into two separate variables. You might also encounter datasets that are missing data for some variables, and some datasets will include outliers. We'll cover techniques for dealing with these situations in this section. You might find that data is missing. For example, some columns in your dataset could be missing data because of a data collection error, or maybe data wasn't collected on a particular feature until the data collection process was underway. Missing data can make it difficult to accurately interpret the relationship between the related feature and the target variable. So regardless of how the data ended up being missed, it's important for you to deal with this issue. Unfortunately, most machine learning algorithms can't handle missing values automatically. You'll need to use human intelligence to update missing values with data that's meaningful and relevant to the problem. Most Python libraries for data manipulation include functions for finding missing data. So how do you decide if you should drop or impute missing values? This question is answered in part by better understanding how those values came to be missing in the first place and how much data the missing values represent within your larger data set. For instance, say the missing values are randomly spread throughout your data set and don't represent a larger portion of its respective row or column. In this case, imputation is most likely the better option. In contrast, say that you have a column or row that has a large percentage of missing values. In this case, dropping the entire row or column would be preferred over imputation. If you decide to drop rows with missing data, you can use built-in functions to do this. For example, Pandas dropNA function can drop all rows with missing data, or you can drop specific data values by using a subset. As an alternative to dropping missing values, you can impute values for those missing values. There are different ways to impute a missing value. For categorical values, the missing value is usually replaced with the mean, the median, or the most frequent values. For numerical or continuous variables, the missing value is usually replaced with the mean or the median. You can impute a single row of missing data, which is known as univariate. You can also do this for multiple rows, which is known as multivariate. We'll now look at a univariate example. Here, the scikit-learn imputer function is being used to impute some missing values. It's a fairly small data set, but there are two missing values. The missing value was imputed by the strategy of the mean. To do this, you first calculate the mean. Here, it's the mean of 3 and 2, which is 2.5. Then you'll impute the mean value for the missing value. Some data libraries include an impute package that provides more complex ways to impute data. Examples include k-nearest neighbor, soft impute, multiple imputation by chain equations, and others. That's it for part 2 of this section. We'll see you again for part 3, where we'll review how to work with outliers in your data. Hi, welcome back. We'll continue exploring feature engineering by describing how to work with outliers. You might also need to clean your data based on any outliers that exist. Outliers are points in your dataset that lie at an abnormal distance from other values. They're not always something you want to clean up because they can add richness to your dataset. But they can also make it harder to make accurate predictions because they skew values away from the other, more normal values related to that feature. An outlier might also indicate that the data point actually belongs to another column. You can think of outliers as falling into two broad categories. The first is a single variation for just a single variable, or a univariate outlier. The second is a variation of two or more variables, or a multivariate outlier. One of the more common ways to find univariate outliers is with a box plot. A box plot shows how far a data point is to the mean for that variable. The box in the plot shows the data values within two quartiles of the mean. Values outside that range are represented by the lines extending from the box, which are sometimes called whiskers. A scatter plot can be an effective way to see multivariate outliers. For example, this diagram shows the amount of sulfates and alcohol in a collection of wines. With the scatter plot, you can quickly visualize whether there are multivariate outliers for the two variables. The origin of your outlier will most likely inform how you deal with it during this pre-processing phase of the pipeline, or possibly later during feature engineering. There are several different approaches to dealing with outliers. You could delete the outlier if your outlier is based on an artificial error. This means the outlier isn't natural and was introduced because of some failure, like incorrectly entered data. You could also transform the outlier by taking the natural log of a value. This, in turn, reduces the variation caused by the extreme outlier value, which would then reduce the outlier's influence on the overall dataset. Finally, you could use the mean of the feature and impute that value to replace the outlier value. Again, this would be a good approach if the outlier was caused by artificial error. This isn't an exhaustive list, but it describes the most common options. After you've extracted features, you'll need to select the most appropriate features for training your model. There are three main feature selection methods. Filter methods use statistical methods to measure the relevance of features by their correlation with the target variable. Wrapper methods measure how useful a subset of a feature is. They do this by training a model on the feature and then measuring how successful the model is. Filters are faster and cheaper than wrapper methods because they don't involve training the models repeatedly. Wrappers typically find the best subset of features, but there's a risk of overfitting compared to using subsets of features from filter methods. Embedded methods are algorithm specific, and they might use a combination of both filters and wrappers. Filter methods use a proxy measure instead of the actual model's performance. They're fast to compute, but they can still capture how useful the feature set is. Here are some common measures. The first is Pearson's correlation coefficient, which measures the statistical relationship or association between two continuous variables. The second is linear discriminant analysis, or LDA. This is used to find a linear combination of features that separates two or more classes. The third is analysis of variance, or ANOVA. This is used to analyze the differences among group means in a sample. And finally, chi-square is a single number that tells you how much difference exists between your observed counts and the counts you'd expect if there were absolutely no relationships in the population. Filters are usually less computationally intensive than wrappers, but they produce a feature set that isn't tuned to a specific type of predictive model. This lack of tuning means a feature set from a filter is more general than one from a wrapper. The filter also usually has a lower prediction performance than a wrapper. However, the filter's feature set doesn't contain the assumptions of a prediction model, so it's more useful for exposing relationships between features. Many filters provide feature ranking instead of an explicit best feature subset, and the cutoff point in the ranking is chosen through cross-validation. Filters have also been used as a pre-processing step for wrappers, which enables a wrapper to be used on larger problems. Wrapper methods use a predictive model to score feature subsets. Each new subset is used to train a model, which is then tested on a holdout set. The score for that subset is calculated by counting the number of mistakes made on that holdout set, or the error rate of the model. Because wrappers train a new model for each subset, they're computationally intensive. However, they usually provide the best performing feature set for that particular type of model or problem. Forward selection starts with no features and adds them until the best model is found. Backward selection starts with all features, drops them one at a time, and then selects the best model. Embedded methods combine the qualities of filter and wrapper methods. They're implemented by algorithms that have their own built-in feature selection methods. Some of the most popular examples of these methods are lasso and ridge regression. They have built-in penalization functions to reduce overfitting. Here are some key takeaways from this section of the module. First, feature engineering involves selecting the best features for machine learning. Pre-processing gives you better data to work with, and better data typically provides better results. Two categories for pre-processing are converting data to numerical values and cleaning up dirty data by removing missing data and cleaning outliers. Finally, how you handle dirty data impacts your model. That's it for section 4. We'll see you in the next video. Hi, welcome back to Module 3. This is section 5 on training. In this section, we're going to look at how to select a model and train it with the data we have pre-processed. At this point, you've done a lot to clean and prepare your data, but that doesn't mean your data is completely ready to train the algorithm. Some algorithms may not be able to work with training data in a data frame format. Some file formats like CSV are commonly used by various algorithms, but they do not make use of that optimizations that some of the file formats like Record I/O Protobuf can use. Many Amazon SageMaker algorithms support training with data in a CSV format. Amazon SageMaker requires that a CSV file doesn't have a header record and that the target variable is in the first column. Most Amazon SageMaker algorithms work best when you use the optimized Protobuf Record I/O format for the training data. Using this format allows you to take advantage of pipe mode when training the algorithms that support it. In pipe mode, your training job streams data directly from Amazon S3. When using the CSV format, the target variable in your training dataset should be the first column on the left, and your features should be to the right of the target variable column. Evaluating a model with the same data that it trained on will lead to overfitting. Recall, overfitting is where your model learns the particulars of a dataset too well. It's essentially memorizing the training data, rather than learning the relationships between features and labels. This means the model isn't learning from those relationships and patterns to apply them to new data in the future. Holdout is when you split your data into multiple sets, commonly sets for training data, validation data, and testing data. Training data, which includes both features and labels, feeds into the algorithm you've selected to produce your model. You then use the model to make predictions over the validation data set, which is where you'll likely notice things you'll want to tweak and tune and change. Then, when you're ready, you run the test data set, which only includes features, since you want the labels to actually be predicted. The performance you get here with the test data set is what you can reasonably expect to see in production. A common split when using the holdout method is using 80% of the data for a training set, 10% for validation, and 10% for test. Or if you have a lot of data, you can split it into 70% training, 15% validation, and 15% test. So for a small data set, we can use k-fold cross-validation to utilize as much of the data as possible, while still having relatively good metrics, in order to choose which model is better. K-fold cross-validation randomly partitions the data into K different segments. For each segment, we'll use the rest of the data outside of it for training in order to do a validation on that particular segment. Let's look at an example. Here we have a 5-fold cross-validation. The available training data is separated into 5 different chunks. For the training of the first model, we're using all those chunks as the training data, and then we're going to calculate the metrics on this test piece. For the second model, we're going to use these pieces as training. After the model is trained, you apply it to this test piece. We do the same thing 5 times. We use all the training data and we test it on 5 different models on different chunks of the test data, eventually testing it on all data points. One other thing to note about splitting your data in a specific order can lead to biases on your model. This is especially true if you're working with structured data. For example, the wine data is ordered by the quality column. When you run your model against your test data, this ordered pattern will be applied, biasing the model. It might also mean that some targets are missing from the training data. Typically, randomizing your dataset prior to splitting is sufficient, and many libraries will provide functions for this. With smaller sets, it is sometimes useful to use stratified sampling. Stratified sampling ensures that the training and test sets have approximately the same percentage of samples of each target class as the complete set. An internet search will give you many ways to shuffle and split the data. One of the easiest is to use the train, test, split function from sklearn. Amazon SageMaker provides 4 different ways you can train models. The built-in algorithms available can be easily deployed from the AWS console, CLI, or a Jupyter notebook. Containers are used behind the scenes when you use one of the Amazon SageMaker built-in algorithms, but you do not have to deal with them directly. Amazon SageMaker supported frameworks provide pre-built containers to support deep learning frameworks such as Apache MXNet, TensorFlow, PyTorch, and Chainer. It also supports machine learning libraries such as scikit-learn and SparkML by providing pre-built Docker images. If you use the Amazon SageMaker Python SDK, they are deployed using their respective Amazon SageMaker SDK estimator class. If there is no pre-built Amazon SageMaker container image that you can use or modify for an advanced scenario, you can package your own script or algorithm to use with Amazon SageMaker. You can use any programming language or framework to develop your container. For an example, if your team works and builds ML models in R, you can build your own containers to train and host an algorithm in R as well. Someone else may have already developed and tuned a model. It is worth looking in the AWS Marketplace to find available models. Amazon SageMaker provides high-performance, scalable machine learning algorithms optimized for speed, scale, and accuracy. For supervised learning, Amazon SageMaker includes XGBoost and linear learner algorithms for classification and quantitative or regression problems. There is also a factorization machine to address recommendation and time series prediction problems. Amazon SageMaker includes support for unsupervised learning, such as with k-means clustering, and principal component analysis, PCA, to solve problems like identifying customer groupings based on purchasing behavior. Finally, there are a selection of specialized algorithms for processing images and other deep learning tasks. Let's look a little closer at 3 of the most commonly used built-in algorithms and their use cases. XGBoost, or Extreme Gradient Boosting, is a popular and efficient open source implementation of the gradient boosted trees algorithm. Gradient boosting is a supervised learning algorithm that attempts to accurately predict a target variable by combining an ensemble of estimates from a set of simpler, weaker models. XGBoost has done remarkably well in machine learning competitions because it robustly handles a variety of data types, relationships, and distributions. The large number of hyperparameters can be tweaked and tuned for improved fit. This flexibility makes XGBoost a solid choice for problems in regression, classification, binary and multi-class, and ranking. The Amazon SageMaker linear learner algorithm provides a solution for both classification and regression problems. With the Amazon SageMaker algorithm, you can simultaneously explore different training objectives and choose the best solution from your validation set. You can also explore a large number of models and choose the best one for your needs. Compared with methods that provide a solution for only continuous objectives, the Amazon SageMaker linear learner algorithm provides a significant increase in speed over naive hyperparameter optimization techniques. K-means is an unsupervised learning algorithm. It attempts to find discrete groupings within data where members of a group are as similar as possible to one another and as different as possible from members of other groups. You define the attributes that you want the algorithm to use to determine similarity. To train a model in Amazon SageMaker, you create a training job. The training job includes the URL of the Amazon S3 bucket where you stored the training data, the URL of the S3 bucket where you want to store the output of the job, the Amazon Elastic Container Registry path where the training code is stored, the compute resources that you want Amazon SageMaker to use for model training. Compute resources are ML compute instances managed by Amazon SageMaker. Amazon SageMaker provides a selection of instance types optimized to fit different machine learning use cases. Instance types comprise varying combinations of CPU, GPU, memory, and networking capacity, and give you the flexibility to choose the appropriate mix of resources for building, training, and deploying your ML models. Each instance type includes one or more instance sizes, allowing you to scale your resources to the requirements of your target workload. Some key takeaways from this section of the module include split data into training and testing sets helps you validate the model's accuracy. K-fold cross-validation can help with smaller data sets. Two key algorithms for supervised learning are XGBoost and linear learner. Use K-means for unsupervised learning. And use Amazon SageMaker to train models. That's it for Section 5. I hope to see you in the next video.